Welcome back to Algorithms and Uncertainty. Today and also in the following lecture, we will get to know some basics of online convex optimization. This is a generalization of the online learning problems that we've seen so far, particularly the experts problem. And on the way, we will then see new algorithms for this online convex optimization, which will eventually turn out to be also generalizations of the multiplicative weights algorithm that we got to know for the experts problem. But before we get there, before we get to the full generality, let's first consider a very simple motivating example, which we can also capture by using this framework of online convex optimization. Namely, my motivating example is online regression. So I guess you know the regression problem. You will have seen this maybe in high school, maybe in a class on machine learning, or whatever class. The idea is in the offline problem that, well, in this very basic case, you have these points, and now each of these has an x-coordinate and a y-coordinate. And you now want to find a linear or affine function that predicts for every x value, it predicts the respective y value. So this is the solution for this particular instance here. And generally, you are given in the offline problem x1, y1, x2, y2, and so on. And we can, for example, have that these x's are real numbers, and also the y's are real numbers. And then what do we want to do? We want to find w1 and w2, which will be real numbers, so as to minimize the sum of the squared errors. So we interpret this w1 as the slope of this line, the w2 as the y-intercept, and we now ask how close is what this red line prediction tells us to the respective y-coordinate. So in this particular picture, maybe this here is the respective y value. So this would be now one of these pairs, xt, yt. And what we're comparing is how big is the distance between these two. And we're taking the sum of these squares of the errors. So this is a standard problem in statistics and machine learning. Now we want to turn this into an online problem. And how will we turn this into an online problem? Rather than being given all of these points in advance, what we are given is always one of these pairs at a time. Well, not exactly. we are always given one x value. We'll have to predict the respective y value. Then we get to know the respective y value, and then we move on to the next. So in the online problem, we'll have in step t, we will get to know xt. Then we have to predict a y value, and then we get to know yt. So I hope you realize that this is very similar to the experts problems that we've seen. There, in each step, we also had to choose one of our experts. Now, what we're in this way of phrasing it, we would have to predict now this y value for the current point that we are currently seeing. And what would be our overall benchmark? Our overall benchmark would again be the best way of choosing W1 and W2. And by that I mean we are only interested in the best single choice of W1 and W2 for the entire sequence, and of course not the best choice of W1 and W2 for every single round. So this will not change between rounds, just like our choice of the expert. We also wanted to just have one single expert for the entire sequence. This was what we were comparing ourselves against in the regret. Now also this problem can be captured by the problem of online convex optimization, and let's now introduce this formally. In the general problem of online convex optimization, we are facing a problem like in the expert setting, where in each step we'll have to predict or make a decision which of the available options would be best for this particular round. And only then we get to know how good they actually are. But in contrast to how we phrased the expert setting, we now won't have a finite number of choices, but rather we are just choosing a vector from an infinite set of vectors. So this is what it looks like. There are n functions. No, they are capital T functions, f1 through f capital T, each mapping from a set S to the real numbers. S is a subset of d-dimensional real vectors. And in each step T, the following happens. We have to choose a point WT from S, and then we incur cost of ft of WT, and we get to know the function ft. So this is actually pretty similar to what we've seen in the context of the experts problem. There we would have captured probably S just as a finite set, and then we would choose one of these experts. We would incur the respective cost of the expert, and then we get to know the entire cost vector there, which is now a function. But actually we will capture this experts problems in a different way. We'll come to this in a second. Before that, let's first say, what is our benchmark? Our benchmark is the regret. And the regret at time t is take the cost that we are incurring minus the cost of the best single vector that we could have chosen. So here again, the minimum is outside the sum, so this is the best single choice for all rounds. And it is not that we may choose a different UT for every step. This would be a much stronger benchmark, but here rather we're just asking for the best single one for the entire sequence. Let's see a couple of examples. And let's first talk about the experts problem. As I was saying, one way to capture this would be to say S is just the set of all experts, or we would have just a finite discrete set, but this is not what we're doing now. We'll rather do this as follows. We'll let S be the following set. Take the set of all d-dimensional vectors such that all components are non-negative and all components sum up to 1. Now I hope you realize this here is nothing but a probability distribution over the d-dimensions. And what we now think is that each of these d-dimensions corresponds to one of our experts, and this is what we can capture by setting ft of v equal to, take the sum over all dimensions, lit times vi. So this is a linear function now, and what we did was we didn't say you have to choose one expert definitely, but you can rather define a probability distribution over the experts. This is what is allowed by the set S. This of course still allows you to just choose one of the experts deterministically, which would be just a corner point of this d-dimensional simplex. But you may also choose a probability distribution, and then what is this ft of v? Well, this is just the expected cost that you're incurring under this probability distribution. And we see, okay, this is actually the kind of an algorithm or the kind of a problem that we've been solving all along, because we were always defining probability distributions over experts, and this was what we were comparing ourselves to, or what we were using for our algorithm design all along. So now this is explicit, we may just use probability distributions over experts. Now let's see a second example, namely, let's talk about this simple linear regression. So this was my introductory example, and there I would set S to be just the two-dimensional real, to the set of all two-dimensional real vectors. And W1, W2 in S, what does this mean? This corresponds always to the slope and the y-intercept of the regression line. And what should our function ft be like? ft, this will depend of course on w1 and w2, the choice that we make in this particular step. This will be w1 times xt plus w2 minus yt, and all of this squared. This is exactly that the error that the regression line represented by w1 and w2 makes on xt, yt. So this is maybe a little surprising how we are now capturing this, because the way I was originally stating the problem was you get to know this x, and based on this x you now have to predict the y. Now what I'd like to do instead is I'd like to say, okay, you just predict a regression line. You just tell me, okay, in this step I want to use this particular regression line, and then based on this, this is the error that you're getting, the squared error. How far are you away from the regression line, or how far is your regression line away from the actual point. One thing to notice here is that this function f depends on w1 and w2, so this is what it takes as the input. And then we also have this y, this x and this y showing up here. Those are just parameters of the regression line, of this error function. So this is not what we're choosing. What we're choosing is always what we're putting into the function here, and this will be w1 and w2. So if this is too complicated for you, it's usually just enough to think about the expert problem, but the difference is now, well, the sets S, this does not have to be just a probability distribution over experts. This can be a different set. And also this function, this will not be a linear function, but something more general than that. But neither of the two can be arbitrary. We will assume that both of them are convex, so that both the set S and the function ft are always convex. And let's first refresh our memories what convexity means, or maybe if you've not seen this before, let's try to understand this. In online convex optimization, we're assuming that the functions are convex and also the set that we're optimizing over is convex. What does this mean? Well, let's first talk about a convex set. So we assume that S is convex. And what does this mean? This means that for all u and v from the set S, and for all lambda which are somewhere between 0 and 1, we have that lambda times u plus 1 minus lambda times v is still in the set S. So the picture to have in mind is that this kind of a set is a convex set, whereas this kind of a set is not convex. Because on this left picture here, if this is the point U and this is the point V, then this connecting line somewhere leaves the set S. But this will not be happening here on the left-hand side. There, this connecting line will always be inside the set. Good. The other thing that we assume is that Ft is differentiable and convex. So this differentiability, that's actually not important, but this just simplifies our exposition here. But what does it mean for a function to be convex? Well, let's first consider the case that S is something like the real numbers, then a function can be easily drawn. So what would a function look like? A convex function would look like something like this. So here I'm drawing f of x, and this is x. Why is this function convex, or what do we require from a function to be convex? Well, one way to state this is that between any 2 points, the function has to lie below the line connecting these points. So here, this is the line connecting the 2 points, and the function is always below this. But this is not the property that we will be using. We will rather talk about tangents. Namely, what we'll be talking about is this property. It's equivalent to this definition that the function graph always has to be below these connecting lines, but what we're now asking is that the function is always above each of these tangents. So what does this mean formally? For all u and v, we would want that f of u is at least f of v plus the derivative of f at the point v times u minus v. So this red line here, this is exactly f of v plus f prime of v times u minus v. If this here is the point v. Good. So we will be considering this kinds of functions which never fall below their tangents. Of course, if your function is a straight line, then this is trivially fulfilled. But you may also have like this, which looks maybe like a quadratic function or an exponential function, and then you still have this property that the function never falls below any of these red lines. So you would have here and here and everywhere you would have such a red line, and the function would never fall below this line. And this definition easily also extends to multiple dimensions. Then, of course, we won't just have this tangent line, but we'll have instead a tangent hyperplane. So, more generally, if S is a subset of R to the D, then what we require is that f of u is at least f of v plus the inner product of the gradient of f at v and u minus v. And here, by this notation, I mean the inner product, so I'm just taking the sum over all coordinates xi times yi. And this, I hope you realize, is just the generalization of this here, because recall that the gradient is nothing but the vector of all partial derivatives. So visually, this looks very similar to this picture that we've seen here. Namely, it looks like this. So here you see a typical convex function, which also never falls below the respective tangent hyperplanes. In this case, you now see just one tangent hyperplane and how this function does not fall below it. There's this one point at which the two intersect, and otherwise the convex function is above this tangent hyperplane. Let's now come back to our examples. Is this fulfilled? Do we have a convex set and do we have a convex functions? Yes, both is fulfilled. So here it's pretty obvious that we have a convex set. Here, this is something that you might want to verify if you've never done this, that this set S is also a convex set. The reason being, if you take two vectors which correspond to probability distributions, then taking lambda times the one vector plus 1 minus lambda times the other vector, eventually what you're doing is nothing but taking drawing from one of the distributions with probability lambda and drawing from the other distribution with probability 1 minus lambda, which means nothing but that you're again defining a probability distribution. Now here it is kind of obvious that we have a convex function. Why is this? Because we have this property that we were requiring, that the function is always above its tangent hyperplanes. This is here fulfilled with equality because this is a linear function. So if you take the gradient here, this will be exactly the vector LT. And so this condition that we were stating, this holds here with equality. Here it's not as obvious. Here we would have to go through some math to actually realize this. The easiest way probably to do this is to see that, well, this what you have here in the inside, this is a convex function because it is linear. And then if you apply a monotone convex function on a convex function, you'll again get a convex function. Cool. So this is the general framework that we're talking about. Now let's talk about what a possible algorithm might look like for this setting. Let's now get to know a very simple algorithm for this online convex optimization, which will turn out to be not quite what we're looking for, but only a minor tweak will turn this into a super smart and general algorithm. So what's the easiest thing to try? Recall that in every step we have to choose one of the vectors. We incur a cost which depends on the function evaluated on the point that we've just picked, but we don't know the function when we're picking the point. Only afterwards we get to know the function. Now what could you do? One thing that you could do is try using the vector or one of the vectors which have been the best up to this point, which means nothing but following the leader. So more formally, in step t, what we do is we set Wt to V such that the sum of the costs so far is minimized. So the first point is arbitrary because there this sum will be empty, so let's not be confused here. So what's the idea behind this? The idea is that, well, eventually we'll have to find this one point that we're happy with, or this is what we're being compared to, this single point that is best for the sum of the functions. So this feels to be a reasonable approach, but what we would actually like to do is we would like to include also the function t in ft in here, the function in the tth step, which we're actually evaluated on. Of course, if we knew the function, then we would just minimize the function ft in that step and not bother about this. But what we will be able to show is that indeed we can bound the regret of this algorithm in terms of the distance between Wt and Wt plus 1. And why do we care about Wt plus 1? Well, in Wt plus 1 we suddenly include the tth step also in this sum. So this corresponds to the cost that we're actually incurring in the step t. Namely, what we will be showing is the following lemma. For follow the leader, we have the following regret bound. The regret of the overall sequence is no more than take the sum over all time steps and take the difference of ft of Wt and ft of Wt plus 1. So this point, Wt, or ft of Wt, this is the cost that we're incurring in step t. But we are now bounding the regret in terms of, well, what is ft of Wt plus 1? So the principal idea that you should have in mind here is that if Wt and Wt plus 1 are close to each other, then the regret is small. So the only way the regret can become large is if the two of them are far apart. Let's prove this. What do we have to show? We have to show that for all t, the following is true. Take the cost that our algorithm incurs minus what's the best point for that sequence. So this is on the left-hand side, this is the regret. And of course we want to bound this by the term that we have here on the right-hand side. And what does this mean? Well, so once again, this is the regret by time t, and this is what we want to bound it by. And now we see, okay, here, this and this is just the same. So this is equivalent to showing that the best point incurs a cost of at least, take the sum over all time steps, and what is ft of wt plus 1? In other words, this shows nothing but that if we were not always too late by our follow the leader algorithm, if we were including also the function ft in the definition of follow the leader, then our cost would be smaller than the best point, so our regret would be 0. Good, so this is the inequality that we want to show. And how do we do this? We do this via induction. This statement is, first of all, trivial for capital T being 0, because then these sums are both empty, and therefore we just have 0 should be at least 0, or negative infinity should be at least negative infinity, depending on how you define the value of an empty sum. No, I guess you usually take this as 0, but then it's just 0 should be at least 0. Good, let's now consider some t which is strictly greater than 0. What do we have by induction hypothesis? We have that if we were taking this sum here, which I've not yet talked about, this will be at least this much. And now this is where the induction hypothesis comes into play. Here on the right hand side we use the induction hypothesis, namely for t minus 1 this inequality is true. Now what is it that I'm doing here? Well, this is just taking the minimum over all possible points u. So I might also take one particular point, which I want to take as wt plus 1. This is one particular point, so this is also true. And why is it that I'm doing this? And this is exactly what the algorithm, this point is exactly what the algorithm will be choosing next. So let's add ft of wt plus 1. This is not in this sum, neither in that sum. But then this perfectly adds to both of the sums, because now we have here the same kind of a term, but just for small t being equal to capital T. And similarly, we also have this for the right-hand side. Because this is also the term that I would get for this sum here, for small t being equal to capital T. Good. Now, how was this Wt plus 1 defined? This Wt plus 1 is defined so that this thing here is minimized. Meaning that this here is nothing but the minimum over all u in S, the sum of all ft of u. And now we realize, okay, this is exactly what we're looking for, because this is exactly the bound that we're claiming up here. Now I did something wrong. Here this should be a small t, not a capital T. It's really important to not mix up the two here. Here we have a small t, here it is a capital T. But this now shows exactly the claim that we had here. Good. So there's the unfortunate thing about every induction proof, that it is a little unintuitive. It doesn't really give us any real intuition about what is happening. The intuition that you should keep in mind is that if we were to include the tth step in this definition of follow the leader, which would actually not mean follow the leader, but be the leader, choose the vector which is the current, or which will be the best after this step, then you're not getting any regret. And this is something that you can figure out quite easily. But this is something that we cannot do. We cannot be the leader because we don't know the function ft in step t. We only know all functions before step t, and this is why we want to apply follow the leader. Is this follow the leader a good idea? Well, unfortunately, not quite, because it can happen that Wt and Wt plus 1 keep jumping around, and then it actually happens that our regret gets big. Let's see what I mean by this. I want to set S to be the closed interval from -1 to +1, and I want to set f1 of w to be w over 2, and then I'll have f2k of w to be minus w, and f2k plus 1 of w to be equal to w for all k. So the first function is a linear function with a slope of 1/2. The second function is a function with slope of -1. The third function is again a function with slope +1. And then we have -1 plus 1, -1 plus 1, and so on. What does this mean? What will follow the leader do? What will it do, for example, in the first step? Okay, in the first step we said it's choose something arbitrary. In the second step, it chooses the function that minimizes this here. How do you minimize the function with slope a half? Well, you go to the leftmost end of the interval. This is how you minimize this function alone. Now, what will you do in the third step? Oh, by the way, what's the cost that you're incurring now? Because you're going to this -1, you're incurring a cost of 1. Because you're exactly at the point where this function is largest. Now, what happens in the third step? What do? You now minimize this plus this, which will be exactly a function of slope minus a half. Whereas this minimized, it is minimized at +1. And we'll see the same thing happens again. We're jumping to the point where it has the highest cost. And also more generally, we have that in odd steps t, the function that we're minimizing is this function of negative slope, and this causes our algorithm to choose the point 1, whereas in even steps, this here is w/2, which makes our algorithm choose -1. So this tells us that ft of wt will be equal to 1 for all t except for maybe the first step in which we didn't actually define what the algorithm is doing. But what is the minimum of all these? This is at most 0 because we can set u to be 0. Which means that the regret of our algorithm is huge. It's at least t-1. Good. So this feels very disappointing. Apparently the algorithm was actually not such a, bad choice because we were able to bound the regret in some way, but then on the other hand there's a very simple example like this where we just keep jumping around and we're always just one step late. And the bound that we were proving showed us that, okay, if wt and wt plus 1 are close to each other, then the regret will be small, but exactly this is not happening here. We keep jumping around, and this is why the regret becomes large. And now we will modify this follow the leader algorithm so that we stop jumping around. What we want to do is we want to add some regularization, which kind of moves us, in this case, just to the center, or effectively just to any point. We just get a drift to a certain point so that we don't keep jumping around, which was, by our lemma, exactly the reason for our algorithm to have a high regret. We now want to modify our algorithm follow the leader slightly so that it actually becomes a good algorithm. And this algorithm is called follow the regularized leader. What is different? We add some term to our function by which we choose the point that we are choosing for the tth step, namely to penalize extreme values. More precisely, this looks as follows. In step t, what we do is we choose Wt as the V that minimizes R of V plus the sum of the cost functions so far evaluated on V. And what's this R of V? This is a regularizer. So R will be a function mapping from S to the real numbers. And what's the idea behind this regularizer? We want it to, well, keep us away from extreme values. So like in the previous example, it should prevent us from taking this -1 and +1 and rather move to 0. And this is exactly what typical examples of regularizers do. Let's see two typical examples. We can use Euclidean regularization. Namely, R of V is then 1 over 2 eta times the sum of all Vi squared. So eta in this case is again a constant. It is a scaling factor. And if eta in this case would be infinite, then this does not play a role. We are playing follow the leader. But if eta is, for example, very close to 0, then we are only using this regularization. All we would be doing would be, in this case, to always play 0. For example, if the 0 point is included in the set S, and eta would be very close to 0. So this has the tendency to move us all to 0 by our choices. Because whatever is bigger than 0, well, is penalized by this function. And we can also talk about entropical regularization. There we would set R of V equal to 1 over eta times, not the sum of the Vi squared, but rather the sum of the Vi times ln Vi. So this function is not defined for negative Vi. And what does this look like? It's always a little confusing because, let me at least try to visualize this here, what this function looks like. This is actually negative for at least everything between 0 and 1. It's a function that looks like this, where here we have 0, and here we have 1, and then it gets positive. So if we're allowed to choose something between 0 and 1, it takes us it keeps us away from taking this all 0 or all 1, but rather moves us to the center. It's actually not symmetric, not as symmetric as I drew it here. You can even figure out what the minimum of this is. It is 1 over e. Why do we care about this entropical regularization? This feels a little contrived, doesn't it? Why care about this kind of a function? Well, we've already seen the algorithm, which is follow the regularized leader with entropical regularization in the expert setting. Because in the expert setting, you can figure out what does it mean to minimize this function here, this entropical regularization plus the cost that we've seen so far. And what is it that we're getting? In the expert setting, WIT will be proportional to the exponential function applied on minus eta times the points and the sum of all time steps before that, Li at time t prime. Does this look familiar? Well, maybe not when I write it this way, but maybe it does, because this is exactly the multiplicative weights update rule. Here we are, or to compute this, you would just multiply this 1 minus e to the power of minus eta times Lit. And this is exactly what also comes out of the entropical regularization when you plug it into the follow the regularized leader algorithm. This is something that you can verify. We won't do this here in class. And our hope is now, by using more generally such regularization methods, that we can generally bound the regret. And this is indeed true. Most of this we will prove next time, but let's first see why in our particular example where follow the leader failed, where follow the leader had this enormous regret, we can now get actually a small regret with regularization. So what was this example? This example was this. We have the interval between 0 and -1 and +1, and our functions are always, the first function is w over 2, and then we'll have minus w and plus w in even, respectively, in odd steps. Now, what would you do now with regularization? Let's talk about Euclidean regularization here. So with Euclidean regularization, what do we get? Let's first consider an odd time step. What is then the function, or let's first write this. We are now having again the function Rw plus the function so far. And how big will this be now? This will be minus w over 2 plus 1 over 2 eta times w squared. And how would you minimize this? You would actually get that you would choose w at time t to be eta over 2. It's just something that you can solve for yourself. Which means that if eta is small enough, then we're not taking such an extreme value, but we're very close to 0. And analogously, we get this in even time steps. we'll get now w over 2 plus 1 over 2 eta times w squared. And if you minimize this, then what you get is that you'll be choosing this to minus eta over 2. So the idea is that if eta is small enough, then you keep close to the origin. And being close to the origin seems to be a good idea here. Good. But what we are of course also doing wrong here is that we are minimizing, or that we take into consideration this regularizer, which is actually something that we never had to minimize in the first place. This is something that this benchmark, of course, will not have to be minimizing, will not have to pay for. But nonetheless, we are now able to extend our analysis of follow the leader. I hope you recall our statement there. This was our statement, which gave us a bound on the regret of follow the leader. We will now be able to extend this to follow the regularized leader. And let's do this. For follow the regularized leader, we have that the regret at time t is no more than, take the maximum of all function values of the regularizer minus take the regularizer at w1 plus ft of wt minus ft of wt plus 1. It actually seems that we've not gained anything, because this looks worse than the bound that we had for follow the leader. For follow the leader, our bound only included this part and not this part here. But the point is, and this is what we're hoping to achieve by the regularization, that these points now change. What our algorithm chooses now more has the property that it never makes these big jumps. That wt and wt plus 1 keep being close to each other. So then this part here will be small, and then we also hope that our regularization isn't too strong, which means that also this is not too big. And this is where you see this eta will come into play. If eta is very small, meaning the regularization is very strong, for example, that we always want to choose the origin, then this part here will be huge, this part will be 0. Or we might set eta to be super large, in which case this here might become 0, but then here we are back to just follow the leader. So how do we prove this? The interesting thing is that follow the regularized leader we can actually understand as follow the leader, but we have a hypothetical step 0 in which the function is just the regularizer. So this lemma from above tells us that the difference between the cost that our algorithm incurs and the cost of any single vector u is at most the cost that Wt causes on Ft and minus the cost that Wt plus 1 causes on Ft. And this holds for all possible vectors u, because it even holds for the u that minimizes this in here. Good. Let's now take this apart and let's just move out the regularizer. So the regularizer was this hypothetical step 0. Let's move that out. Fantastic. Now what do we have? We have this here and this here, which is just the same. So what we have is that sum of all these ft of wt minus ft of u, this will be at most r of u minus r of w1 plus the sum of these differences. And this holds for all u. So what we're getting is that the regret at time t, this is exactly the maximum of what we now have on the left-hand side. This is at most, well, the maximum of what we have on the right-hand side. And there it is only the r which includes a u. Or the first r to be precise, the second r even doesn't include it. Good. And this is exactly what we wanted to show. We showed that the regret is at most the maximum value that the regularizer takes minus the regularizer evaluated on which to take in the first step plus this sum of these differences. Good. So, the question is, of course, which regularizers are good? Is Euclidean regularization good? What value of eta would it make a good regularizer? This is exactly what we'll talk about next time. Because what do we have to talk about? We have to talk about, on the one hand, what will these values be? What's the maximum and the minimum value that a regularizer takes? The further they are apart, the bigger our regret becomes. But at the same time, why is it that via regularization, WT and WT plus 1 get close to each other? And introducing some further assumptions next time, we will be able to actually show that this does happen, that WT and WT plus 1 will always be close to each other, which gives us a bound on this sum here. Yes, all of this we're continuing with next time. I hope you enjoyed today's lecture. As usual, please do reach out to me if you have any questions. See you next time. Stay safe. Bye.